All right, in the second example, we're going to continue to just focus on setting these up. So please, in your homework, continue to practice your integration. Expect to be asked on tests to actually show the integration here, but that should all be old news that we're just practicing and trying to make sure we're still good at. So I want to focus on the setting up. Okay, so I'm giving you a region, and I'm going to use this region for many parts of this. I think I have like 6 different parts. This one's a little different from the pictures we were looking at before, in that we're looking at the region tracked between 2 curves instead of between a curve and the x-axis. Technically, you can consider the x-axis a curve, but it's kind of a boring one. So here's my region, and it's a little skewed. You can see that this is right here, this is x equals 2, and this right here is y equals 2. So it would actually be a little taller and skinnier, but this will make it a little easier to draw. So first thing we're supposed to do is take this region and spin it around the x-axis. Down below you can see that I have stuff hidden from you still. That's a computer-generated version of this, which might end up looking a lot prettier than mine, but sometimes also it's a little hard to tell what's going on. So if I'm going to spin down, I'm going to have this bottom corner end up at 2, -8. Alarm's going off. Okay. There we go. And then the inside as well is going to be determined by this curve part. And remember, only the shaded part is going to create volume. So we're going to have this perfect cone as the outside of our shape. And then on the inside, oh no, we're going to have, oh man, I can't snag this thing. There we go. Maybe we'll use the bright color. We're going to have a funny hollow. I said funnel shape on the last one, but this is kind of funnel shape as well, like a whirlpool, sideways out of the middle. So nice, flat, perfect cone on the outside, but this kind of funny, bulged out inner part so that the inside is not a perfect cone. So it's kind of a funny bowl vase shape that we're working on. Okay. So if we take a slice, and it's definitely going to need to be a vertical slice, and we remove it and we look at it, we're going to have a washer. This does have a hole. And we will need to find the inner radius and the outer radius. So in my picture, the inner radius, we always start from the axis of revolution, which in this case is the x-axis. And we go up to, for the inner radius, we go up to the bottom curve. The bottom curve is going to determine the inner radius. So whatever x value I'm at, if this is my x sub I, here, let me label them. The top one is y equals 4x. And the bottom one is y equals x cubed. So whatever xi I pick, the height of this thing right here will be that xi cubed. My formula tells me that my y is always my x value cubed. So that's my little r. My big R, I want to do the same kind of thing. We'd start at the same x value, but it looks like I was a little crooked. And we would want to run all the way up to the top. And we don't need to subtract off the xi. The outer radius is that entire thing, and that's going to be determined by the top curve, which is y equals 4x. So that will be 4 times x sub I. My y value is always 4 times as big as my x value for the outer curve. So to figure out the volume of this whole thing, the volume of my one slice is going to be pi times the outer radius squared minus, times height, delta x, minus pi times the inner radius squared times my height. So when we go to set up for the entire volume, I'm going to move the pi out in front. You don't have to, but I just like cleaning up wherever possible. So this is going to become a 16 xi squared. Down here we won't need the I anymore because we're doing every single x value. And then this is going to be an xi to the 6th. And we need to start at 0 and stop at 2. Oh, and I didn't mention this, but I think we should have it from earlier sections. If you weren't provided with a picture, you might need to set these two equal to figure out exactly what that point of intersection is, but our picture made it pretty clear, and you can check easily. If you plug 2 in, both will give you a y value of 8. So that's my setup, and it's fine with me if you want to leave the pi in the mix. It's fine with me if you want to keep them separate. I'm mostly just thinking that for the purposes of actually performing the integration, cleaning out as much of that mess as possible will make it a little simpler. Okay, so that's my setup. I'm going to leave the actual solving up to you. For this, oh, that's right, I forgot. Okay, so here I drew my picture, but I do have a computer generated version. You can get Wolfram Alpha to do these. You just tell it basically what we had here. You tell it to rotate the region bounded by y equals 4x and y equals x cubed, and then I think you should probably give it x values. So I think I said between x equals, or probably I said on 0 less than or equal to x, less than or equal to 2, something like that. So I'll probably, on your next technology piece, ask you to play around with that a little bit. Okay, so that's what it looks like, and you can see this is my flat outer piece. This is looking even more skewed because this is my 8 up here. So this is supposed to be the x-axis sticking out, and you can see my linear outside and this funny curved out inner part. Okay, so for the next one, same exact region, but now I want to give myself a little space. So if this is y equals positive 1, we're going to spin around y equals negative 1, which means this hollow of 1 will put me all the way down to y equals negative 2 for this corner. And then it's going to slope down from there. And look, this is rough, but looks something like this. If we're taking this point to 8 and we're flipping it over y equals negative 1, it's actually 9 units up. So that's super crooked. Hold on, it's bugging the heck out of me. Okay, that's a little better. So this is 9 units up, which means this should be 9 units down, which puts me at 2. 9 units down from negative 1 is negative 10. And it's going to look somewhat similar, but the radius has gotten a little bigger for this outer piece. Outer is still a perfect cone. And then the inner piece, let me find that bright color again, I liked that. For starters, we'll have, if we're thinking about this as if we turned it on its skinny, this blue circle that I saw, if we're thinking about it as a bowl or a vase, this one's not a very good one because the bottom is hollow. So this one does not hold water. But it does have, once again, kind of a similar inside shape other than that. It's just a stretched out version of the last one. So when we make our slice, it's going to be vertical. And it's definitely a washer. And its width is a delta x. So the volume of my slice is going to be a pi times the outer radius squared delta x minus a pi times the inner radius squared delta x. So the inner radius is going to come from starting at right at the middle at the axis of revolution, that's y equals negative 1, and running up until we hit the bottom curve. So we need to break this into pieces. At the bottom we have a length of 1 just to get up to the x-axis. And then the distance from the x-axis to the bottom curve is going to be an xi cubed. So the inner radius is now, whoa, I don't know why that just made me crazy lines. The inner radius is now an xi plus 1. And then the outer, oh shoot, I started with inner, and I put it in the wrong order. So that's the inner radius, that should go second. The outer radius is same idea, but now I need to go all the way up to here. So I'm going to keep that same 1 to get from the axis of revolution to the x-axis. But now to get up to the top curve, I don't want to go an x cubed, I want to go a 4x. So this is going to be 4x sub I plus 1. And to add all of those up, move the pi out in front, we're going to have, I'll even multiply it out. So we're going to have, oh, not 4, 16 plus 8x sub I plus 1. And over here, we're going to get x sub I squared plus 2x sub I plus 1. So in here, once we remove the pi and the dx, we can actually do some combining there. Say we have a 16x squared minus an x squared, so that's going to be a 15x squared. And again, my goal here is, I don't actually, if I just ask you for a setup, I don't mind if you don't ever multiply this out. But if I actually ask you to calculate the volume, which you'll be doing a fair amount of on your homework, this is going to be the step that's going to help you do that. We have an 8x minus a 2x. And then we have a 1 minus a 1, so that actually drops out, and this works out fairly nicely. So you can see this one is not terribly hard to calculate. We're slicing vertically, so we want to say that our first x value should be a 0, and our last x value should be a 2. And notice the fact that there was a hole, that this thing doesn't hold water, doesn't really affect anything weird in my integral. It shows up right here in the plus 1s that we add to our radius, and well, it's more than just that, I guess. So the spinning around -1 shows up in the plus 1 to our radius, and this subtracting out the inner washer takes care of that. The inner washer never, what do I want to say here? And the inner washer exists all the way from the beginning to the end. The skinniest the inner washer ever, or the inner cylinder ever is radius 1, and it just gets bigger from there. Okay, so there's my computer generated version, if that helps you at all. So this is my y equals -1. This is the downside, is that that's really hard to see, that that's not up at the x-axis. Here's the, looks like the x and the y-axis are there. So you can see again, their scale is a little funny, so it makes it look long and skinny when it's actually pretty tall and flat. But that's the general idea. Nice cone on the outside, and this kind of trumpet shape coming out of the inside. Okay, third one. Now we want to spin around y equals 9. I absolutely did not leave myself room for that, so maybe we'll rely somewhat on the bottom picture. But this is going to leave a hole at the top. There's going to be a gap right here. The top corner of our shaded area is at 2,8. So if we spin around y equals 9, that's going to make a bottom corner for the top part be at 210. If we were 1 below, then when we flip it should be 1 above. And then sort of carry through onto the last page. This should slope back down. If we're spinning around y equals 9, then we should be way up at 18. So this slopes in and hits at 18. And kind of looks funny, but sort of like that. Okay, so this time, since we're spinning up, the x cubed is actually going to be the outer shape. Switch colors. So this one is going to be a nice rounded bowl with a perfect hole cut out of the middle. Still being laggy here. So this inside goes perfect cone. Okay, so when we take a slice and look at it, it's definitely a washer. And it's going to be, since it's a vertical slice, it's going to definitely be height delta x. So our outer radius, when we go back to our picture, remember you always start from the, oh, I guess I usually do my inner radius first. So you always start from the, here's my slice. You always start from the very center, the axis of revolution, and you drop down to, for the inner radius, you're going to drop down to the bottom curve. I know I'm dropping down this time because that's where my original shaded region was. You always want to reference back to that original shaded region because you have equations for all the boundary curves for that. So if I know this is 9, and I know this is, if this is my x sub I, it's from the line, so it's a 4x sub I, then the inner radius is 9 minus 4x sub I. The outer radius, same idea, we want to start from the axis of revolution, but now we have to go all the way out to the outer curve, which is almost at the x-axis here. It's going to be an x sub I cubed. So the outer radius is a 9 minus x sub I cubed. And notice this is what we said earlier, that the outside of the shape is now determined by the x cubed, so the outer radius involves the x cubed. Okay, so the volume of my slice is going to be a pi times the outer radius squared times a delta x minus a pi times the inner radius squared times a delta x. So if I want to add all of those up and simplify a little for future integration, we are going from 0 to 2, and we're integrating a 9 minus x cubed squared minus a 9 minus 4x squared with respect to x. And again, for the purposes of integrating, I would actually FOIL that out. Make sure you FOIL, don't just distribute powers. If you're just asked to set up, this is great. You don't have to do anything more than that for setup. And there is the computer-generated version. So you can see bowl-shaped outside, perfect cone missing out of the middle. Yeah, so sometimes they're prettier. Part D. Hold on, I'm peeking. Yeah, I do have 6 parts. Okay, so part D, we're going to spin around the y-axis. So that's going to flip us across. We're going to have, again, kind of the bowl-shaped outside. Since that was hideous, I'll scroll down. Bowl-shaped outside. This one, for some reason, it decided to make a little bit more reasonably scaled. So that actually is fairly proportionate. And then we have this perfect cone hollowed out of the middle. So our slices, my colors will switch, there we go, are going to be horizontal this time. And there is a hole. There's a hole anytime your region doesn't touch the axis of revolution. So at the bottom, notice our region finally touches the axis of revolution. So this one holds water. There, right at the very bottom, there actually isn't a hollow in the middle. But everywhere else, the region doesn't touch. There will be a washer. Okay, so this is going to be a delta y since we're slicing the other way. And our inner radius, outer radius. So our outer radius is determined by the cubic, and our inner radius is determined by the line. So we know that the line is a y equals 4x, which means, since we're now horizontal, we want the x value as our radius. X is equal to y over 4. So the inner radius goes from 0 out to the x value of y equals 4x, which means inner radius is y sub I over 4. And this is our y sub I that we're picking. Outer radius, same idea. We go from the y-axis to the outer curve. The outer curve is a y equals x cubed, which means the x value on the outer curve is a cube root of y. So this is the cube root of y. We don't need a plus or minus anywhere because we're actually starting at the axis and going out to the curve. Whenever you have that, you're not going to need that plus minus on your radius. Okay, so our volume for this thing is a pi times outer radius cube root of y squared minus a pi times inner radius squared, which means to get the entire volume, move that pi out. This is y to the 1/3 squared. I've seen some people have some fractional exponents confusion. So that's going to be a 2/3. And then we have a y squared over 16. Put that in one integral so that I can just write 1 dx as well. And this time, since it's, oh, watch me writing dx's. Hold on, shame on me all over the place here. These are not dx's, these are dy's. dy. And since we're using dy's, we need to make sure that our limits of integration are y values. So now we're starting at y equals 0, and we're stopping at y equals 8. So that's our integral for that one. There's the other picture of the shape. Okay, so now we want to spin around x equals 2. I think I'm just going to use my picture down here. So this is kind of what it looks like. No, I'm not going to because I find it hard to read where everything is on theirs. So x equals 2 is right here. When we spin around, this is going to land out at x equals 4. And then we'll have the inner curve kind of doing this. And that means the outside is going to be our perfect cone, and the inside is going to be this kind of whirlpool funny shape. So we're going to slice vertically again for this one. And our slice is going to have a hole in it, so it's going to be a washer. And it's going to be delta y tall. The inner radius this time comes from, ooh, and I'm breaking my own rule. Make sure you go back to the original region or it gets really confusing. So we know that this is 2, and we know that this is the x value of the y equals x cubed graph. So, oops, that's not where I want my arrow to go. Y equals x cubed graph, which means, again, x is the cube root of y. So this is the cube root of our y sub I, but that's not what I'm looking for. I'm looking for this little solid region right here. So what I want is 2 minus the cube root of y. That's my inner radius, whichever y I'm at. And then it's a similar idea for the outer radius. So now I'm going to go to a different point just so you can see. I want to start from the axis of revolution, which is x equals 2, and I want to go back to the outer curve, which means that this distance right here is y over 4. We know that the entire distance from the x-axis to the axis of revolution is 2. So the outer radius is going to be 2 minus y sub I over 4. Which means, I'm going to skip a step. Hopefully I won't mess you up. I'm going to go straight to the volume formula. We're going to get a pi r squared minus pi r squared h minus pi r squared h even. I'm going to factor that pi out. So outer radius is a 2 minus y over 4 squared. Inner radius is a 2 minus the cube root of y squared. Oh, I didn't quite leave myself room. That's with respect to y. So again, as soon as you're doing dy's, the limits of integration need to be y values. Okay, I'm doing this all as one big long video. Hopefully you aren't totally tired of listening yet. Last one, we want to spin around x equals -1. So that would be roughly here. And let's see. Okay, so this is 1, which means this bottom corner, when I flip across, will be out 1, so this will be at -2. Bottom corner at -2. The top corner is 2 further than that, which means at -4, 8, we get a top corner. And let's see, flat this way, curved out this way. Okay, so this one's going to be a big, wide, rounded out bowl shape with a big hole in the middle that doesn't actually connect. So this one absolutely does not hold water. So it's got like a coffee filter shape taken out of the middle, and then it's got that rounded out outside. Okay, so last one on slicing horizontally. So when we take that slice out and look at it, it definitely has a hole. I feel like my stylus skills are getting worse as this long video goes. Maybe my stylus is getting tired. Okay, so this is our shape. The inner radius, hold on, I gotta go back and fix this picture. Outside like usual. Okay, so the inner radius is determined now by the, make sure you go back to the original region, the line. And we know that the line is in x equals y sub I over 4. So that would be this distance, right? That's from the y-axis to the line. This is y sub I over 4. This distance right here is 1. So the inner radius this time is y sub I over 4 plus 1. The outer radius is determined by the outside curve. So now we need to take the cube root of y and add that to our 1. So the outer radius is 1 plus the cube root of y sub I. So our volume is going to be a pi times outer radius squared minus inner radius squared. And we're going to start at 0 and we're going to stop at 8. Okay, so there was a whole bunch of different variations on this, and you'll have different regions and things to look at. Hopefully that gets you started. Thanks for watching.